Okay. Yeah, just room here in front of the. So hello everybody. Welcome to this first meetup about data engineering. I would like to make a statement because while I was writing all this presentation, I realized how much of the Google Cloud services we use at Cabify. So I bet I'm sure that we're not receiving any money out of from Google to make promotions. This is not a promotion. It's simply a coincidence. So whenever I'm talking about any product, I will try to give you alternatives from other cloud providers and whatnot. So a little bit about myself. I'm, as JM mentioned, I'm a software engineer mainly. I've been working in the industry for the last 13 years, more or less. Programming, I love coding. And since the last year and a half, more or less, I've been working as a data engineer at Cabify. So I got the chance to learn the ways of data in the current industry as we are. So since this is going to be a talk about data, I would like to start running a query. Okay. Probably most of you know we've been having a strike, a taxi strike going on in Madrid in the last weeks. It's finally solved. But usually those kind of strikes have some interesting consequences for Cabify and other high-rating providers. That for a while we become the top downloaded application in Apple Store and Google Play Store. So the idea is I want to show you how we can get right away some data out of our data warehouse. Considering I'm an engineer, I don't have real access to the BI, Tableaus, or any dashboarding tool, but I can run some queries very quickly. So let's run it away. Let's give it a run. We will try a few seconds. Okay, we got it. And we got the result. This is a simple query in which I'm trying to compare how much rights, how much we have grown during the strike, right? How much we have been working or providing new rights for new customers. So,
sorry, is it possible to switch off the lights?
Can you switch it off, the lights? Okay, so the thing is that, material, right? The thing is that for every week I'm comparing the data before in the previous week with the data the current week. But since we have some disclosure agreements, I cannot show you actual data. It's only terms in percentage compared to the previous week. So the thing is that usually we are like, we grow, but so little. But in the end, since the strike, we grew a lot. So this means that every day we keep growing a lot compared to the previous day. Okay. So this was not, as I was mentioning, this was not always this easy to query on our data warehouse. But just to give you a little bit of an introduction about the Cabify infrastructure, we have, as you know, we have the driver application, the rider application, a bunch of microservices, and then we have CouchDB. So my first question to you people here today is, how many of you have used CouchDB in production? Not so many hands raised. One there. Okay. Yeah, so this is going to be tougher. The CouchDB, it's, for those of you who do not know, it's a document-based NoSQL database, okay? So it does a pretty decent job when it's about retrieving documents based on a key or making range queries on a range of keys. But it's a pain in the ass when you have to run querying on it. The thing is that you cannot run analytics on top of CouchDB unless you create proper views. And that means, by experience, I tell you that if you have a database with with terabytes of data or gigabytes of data, if you create a view out of it, it will tear down your database completely and will break your service. So back in the days when the data analytics at Cabify started, if you find some of the elder people at Cabify and you ask them how hard was it to get some input from the data at Cabify, they will tell you that, yeah, initially we got CSV files gathered out of CouchDB views. So the thing is that it was a really manual job. The data analyst at turn had to find somebody at the engineering team and request them to get some data so they could run some sort of analytics. as I say, that was the Stone Age. Then there was the first breakthrough, we like to call it. It was such a witty piece of software called CouchTab. Our CDO at the time, Sam Lone, he developed himself to solve this one piece of problem. We need a way to move data out of CouchDB and put it in a place where we could easily query in a fine-grained way, let's say. So CouchTab was a really nice tool in terms of it will define a really nice and easy to use domain-specific language. This is an example on how you could, given a document on this CouchDB database, how you could translate that document into a set of columns, or even define relations. When you have a really nested JSON object within your database, you could define for those nested objects, you could define relations and store those in a separate table, for instance. So that's why you get here for a document called Journey Fraud Evaluation. It's an example I got. You got a table called Journey Fraud Evaluation, which has different columns and have a collection of different elements that will go to another table. And automatically, one-to-many relation is created to fetch the data on the nested object. And there was a revolution at the moment because it enabled Cabify to get almost real-time analytics for the business teams to see how the company was going, right? So there is a thing that it's like, this could not be possible if there was not a really nice piece of feature in CouchDB. And it's the fact that you can get almost real time what's going on in the database thanks to the change feed. The change feed, it's a long-standing HTTP request you can do to a particular endpoint in CouchDB, and you will get what's going on, what documents are being created on a database, what documents are being deleted, and which of them are being updated. So you get a log on the history of your database. So CouchDB will populate from that CouchDB feed. As you can see here, you will have a set of CouchDB databases, and you will have different processes reading from those databases and populating a Postgres instance where relational SQL-based queries could be run. And that will lead to having dashboarding tools like Tableau or the like. So the thing is that new data sources were being added, new Tableau books were being created, and the first Postgres instance quickly ran out of resources. Some of my colleagues was telling me today that the first instance was like a 2 gigabyte of memory, whatnot, machine with really low capabilities. So, but it was a good start. So data was added, new books. This is since we were growing in size, our Postgres server, it was a single machine all the time, but with bigger resources. This is a pretty good example on how scaling vertically, it's usually a really bad idea because you're not solving your resource problems, but you are postponing the judgment day. So this is the current server. If this is an HTOP, you can see it's for a 96 CPU, 5 gigabytes RAM, 4 terabytes. I really wish I could play Red Dead Redemption 2 on full graphics on this server and see how it goes. But as you see, currently it's really unloaded. This is the maximum peak of work I could get because it's almost dismantled at the moment. But sometimes when it was in full working mode, usually if you type HTOP, you will see this picture will resemble a Christmas tree. So that's why we call it the Christmas tree as a funny name for it. So things have started changing. We need to find a way to solve this scalability problem. So ideas came up. We started thinking, okay, what if we get all our data sources? Because we don't only have Couch, we also have Amplitude, Zendesk, other third-party tools we use to fetch or to operate. We use to operate our service. What if we get those data and we put them on a topic, on a distributed topic? We can scale horizontally, and on top of that, we can start building things like what if a data lake, data warehouse, an anti-fraud system. So we started prototyping. We created, instead of using Kafka, we thought, okay, what if we use Google PubSub which is a self-service provided by Google, which we do not have to maintain, and our life will be much easier in terms of infrastructure. When we started creating testing this against an anti-fraud system and that rendered to be quite feasible. I mean, the anti-fraud system was a success. So we started thinking, okay, what if we start building the first thing, a data lake? We need the data in a common place, because we had a huge problem at the time. This was being on the table, and was the fact that the data the data science team did not have a common source of data. It was not easy for them to fetch data and use it to run their experiments, right? So what is a data lake? Just probably most of you know, but for those of you who do not know what it is, a data lake is simply a storage in which you save your raw data, usually in a file system, or in a set of files containing blobs of data, okay? You have raw data on a file system, you can fetch at will and do things with it, okay? And the nice thing about it is that you can have duplicates, you can have everything. The more, the merrier there, okay? So what are the ingredients here? You need a stream of data to populate the data lake. You need a file system where to put your blobs of data, and a pipeline usually. A pipeline will be an application that will read from the source and do some sort of aggregations and combine the data and put it somewhere on your file system, okay? So we started thinking, okay, we have different models, different sets of documents. We need to arrange them in a way we can have them like on a granularity of 1 hour, let's say, okay? We could have like, on our file system, we will have a path in which you have, okay, we have the organization, the model, the region this model belongs to, because we operate in different regions, and then a set of dates, year, month, day, hour, and then the files containing the actual data, okay? And at the time we were sure that our file system will be Google Cloud Storage, but if you are on Amazon, you will use S3 or the like, okay? And then one of our biggest problems was to define, okay, how do we run this pipeline, okay? At the time we were pretty familiar with Spark. We were running some batch jobs in Spark to handle some data manipulation. So we had the option, okay, we can have Spark streaming because we have to read from a stream, not the usual batch approach. And we could have a cluster of built on top of Dataproc that will be self-contained, self-maintained. We don't have to arrange it or care much about it. Or another alternative we had, it was, okay, what if we use Apache Beam running in Google Cloud's data flow? That data flow, it's a really neat piece of clustering or running pipelines, because it lets you auto-scale your pipeline depending on your needs, on the amount of data you're processing at a time, okay? So we were discussing, okay, yeah, the things in favoring Spark, where, okay, we are familiar with the Spark syntax. We've been developing already, but we will need to set a cluster, a data per cluster, properly dimensioned. We will be making under usage of the resources of this cluster probably, because there will be valleys, there will be peaks. And we have to be able to cope with the peaks. And things against Beam was like, okay, we do not know Apache Beam, and it's not really one of the most used products in the community of data engineering, right? And also another thing against it was that it was mainly built in Java. There was a Python SDK, but it was like 2 versions below the Java SDK. But we found our folks at Spotify, they have created a layer on top of the Java SDK made in Scala. It's called SCIO, C-S-C-I-O. So we started investigating and thought, okay, let's go for the data flow approach, because in one hand, it's scalable. We don't have to, it's auto-scalable, let's say. We don't have to dimension properly our clusters. And it provides a really mature streaming model. You have different window sets. At the time, Spark streaming was not clear about how to deal with different kinds of windows. And it's portable. That's a pretty neat thing. It's like you can run your Apache Beam pipelines in a Spark cluster using yarn. I will show you later the capability matrix in case you're interested. And it has an appealing syntax. This is a snippet I just got. You will not see something like really out of what's typical in our ecosystem. It's a typical map reduce operation in which we are using SEO here. It works with the idea of having S collections, which is the typical RDD in Spark, for instance. So you have collections of data, and you return collections of data out of the transformation, right? And the nice thing about it is that you usually provide your operations or your transformations with names, because you will see how easy it is to follow up on the data flow interface to see what's going on every step of your transformations. Because every transformation you run here, it will translate into a proper piece of interface you can manipulate and see on the data flow screen, okay? And this is how it looks like. In Python, I really love how you can define your pipelines, because it works like typical traditional piping on your shell. You simply get, in this case, you get the states, which is a big collection of this model, which is something internal, state interval in Cabify. And you apply some windowing to it. Okay, I want to split my data into chunks of 1 hour here. And I want to run my triggers once I at least have one element, or 10 minutes have passed within that window. So with that, you pipe your windowing into your transformations, and whenever you group your stream data, you can then emit the results of running the final transformations on your window data, okay? This is the capability matrix I was telling you about. Like you have these transformations you can run on top of Apache Beam. And these are the Beam runners you have out there. Okay, we're using currently the Google Cloud's data flow, but as I was mentioning, you can run it on Apache Flink, Spark, Apex, all of this. I can show you. I can share if you're interested. I can show you this link if you don't have time to copy it. And this is the final architecture we had with this pipeline. It was like the first thing we did with Apache Flow, so we were having a lot of mistakes when doing it, but we have learned a lot since our first pipeline. So in the end, we have the data source. We have Google's PubSub as a streaming, as a source of stream data. Then we have data flow, which will collect that data, process it, group it, and save it on the proper bucket. And this is our bucket in cloud storage where we save our data. So I will show you the live pipeline in the data flow screen, if it wants to load. But as you can see, there's a pretty interesting thing about this interface in which you can have metrics on how your cluster is scaling up. You can see here like a regular amount of peaks of workers. It's like currently it's running on one only worker, but it got to reach like 3 workers on every peak. That's because we run a batch job every morning, which creates a lot of data. So it populates. Somebody is laughing there because it's responsible for that. So it generates loads of data. So we fill the PubSub topic with this amount of data, and it has to scale up to cope with the load. Okay. So, and then you can go into here the pipeline resembles the typical ETL process, okay? You have we read from PubSub, we do some transformation, we apply the windowing, so we keep files, the blobs of data into the proper folder, depending on the date, and we write the files to the destination, okay? So let me, so the thing is that this was the final architecture. I show you how the job looks like. So, okay, this is how I want to show you a presentation of how the actual data lake looks like. This is more or less the structure we have. It's simply a bucket on Google Cloud Storage. So we have the bucket name, we have the company name, in case we have more companies in the future, which we will, and the model we're analyzing, and then after that, we can see the same structure for all of them. So for instance, if I go and see, let's see, a state interval, which is a piece of data, we use to track where the drivers are. We see that we have state intervals on all these cities here. So let's check, for instance, Madrid. We have all those years worth of data of state intervals. Okay, let's check 2009, 02. What day is today? 13, 12. So today we have all these hours worth of data until 8 o'clock UTC. So let's see, for instance, if I want to show you some data. Well, I will show you first the blob files we have on that hour. You will see we only have the first, because usually we flash our pipeline of data every 15 minutes, okay? So we have 15 minutes worth of data for state intervals in Madrid today at 6 o'clock, okay? If we go 1 hour before, you will see we have 4 files, each for every piece, 50 minutes piece of this hour. There's an interesting thing, I'm not sure I will be able to find now interactively, but whenever there's a problem when you deal with this sort of streaming data is that you have to deal with what Apache Beam calls late data. There are chances that you have closed a file already and you have flashed it to the data lake, but new data that was supposed to be in that folder, on that file, comes through the streaming pipeline. So in that case, you have the possibility to keep the windows you create open and check for new data. And whenever you have new data, you can create new files, which we call late. Okay, so you don't lose the data. So usually you have those 4 files in a row, but also you may have additional late data files containing blobs of data coming late. So let me show you. If we run a cat here, 10 o'clock, and we unzip it, and we can head -1, and we get the first. Do you see that we have all this metadata in raw format about what an state interval is? Let's very print it a little bit so I can show you. In the end, you have we have introduced to every data we save, we introduce this metadata, which is internal to the data lake. So we can keep track and properly route every file into every piece of data into the proper folder within the lake. Okay, so we have the timestamps, the IDs, where it comes from, which database it's coming from, and so forth, okay? So what's next? Okay, we have a data lake going on, running, producing raw data, but that's okay for the data scientists who can grab pieces of data and run their experiments. But what if we need to create fine-grained queries and provide nice dashboards to anybody, not only the business teams, but to anyone in the company interested in seeing what's going on. So we started continuing with the same idea of having our already available PubSub topic and our data lake. We said, okay, we're gonna need a query engine that is capable of running fine-grained OLAP queries, and it has acceptable query times. I mean, by acceptable, I usually mean like less than a minute will be ideal. It has to provide an easy query language so anyone can go to the console and run their queries. And it should be integrable with popular dashboarding tools like Tableau, Data Studio, and whatnot. And for sure, it has to be scalable ad infinitum, okay? So I remember back in the days where this was like January 2018 when we were starting analyzing this problem. And I remember having lots of meetings and discussions about different search engines, database, and so on. Most of them I didn't know, I didn't have a clue what they were about. So just to show you a few examples that we were analyzing. I don't know if you have ever used any of those. Is there an expert on any of them? The thing is that we were testing some of them. I was particularly quite enthusiastic about Apache Drill because Apache Drill comes out of, it's a fork coming out of Apache Dremel, which is the base foundation of Google's BigQuery. It has a really nice approach. It provides a connector to access different file systems, HDFS, also cloud storage. And so we could have like the data lake as our base of data. And on top of that, we could build a cluster on Dataproc to run Apache Drill, because Apache Drill can run as well on Dataproc. So we were testing it. The results were not promising at all. I had like queries for one of our most massive models. We have like response times of 1 hour, more than 1 hour. So that didn't seem like feasible. But we found a way to make it run faster. If we turn that raw data in the data lake into a Parquet format set of files, it will run like much better, but it wasn't enough. You could have a query in like 15 minutes out of those massive data we had. So then we discard Apache Drill. We had a look at Impala, which seems like pretty nice. It supports SQL-like languages, but it does not have a really well-tested connector for Google Cloud Storage. So we discarded. Then we were checking Druid, which is an amazing database. It comes with a lot of fancy features. It seems like, in a way, a way to go for analytics in the future. I probably will have the time, if we can, to give it a try. But it does not. It seems to be more suited for time series data, and it does not provide a common query language. It's easy to use. It provides a really custom thing, sort of Elasticsearch-like or Lucene-like query language. So then we had like those two Google Cloud products, Cloud Spanner, Google BigQuery. We were checking both of them, and we found that Cloud Spanner is more suited for, not for OLAP, but for OLTP transactional queries, okay, in a consistent way. So in the end, we say, okay, seems like BigQuery seems to be the right tool for running OLAP queries. So we adopt this BigQuery database as our source of data warehousing. And the next problem we had to face is how we normalize raw data we have in our data lake or in our company, where no models exist or they're not easily exploitable. So we started creating Scala classes, perfecting all the information we had in the models at the company. But we soon discarded that because we found that anytime somebody change a model, we will require a new restart of a new redeployment of the data pipeline, which seemed not to be a good approach in terms of maintenance. So we said, okay, what if we use protobuf to define our models? We had so many models that it was not easy. There was nothing like reflecting the structure. So creating a protobuf about all of them seemed to be like a tough approach. It will provide like really a contract, but it will also imply that we will have to create a protobuf for all the models in the company, and we didn't have time for that. So in the end, we said, okay, we have BigQuery. What if we use the BigQuery schemas as the source of definition of our models? Those BigQuery schemas, since they are a simple JSON file containing the structure, we could use versioning on them. We could have them on a repository where we can handle. So I can show you here an example of a user. You define typical variables, data, attributes, the type of attribute, if it can be nullable. You can have like, let me show you records, which will be nested and whatnot. So you can represent a JSON object using this JSON notation out of BigQuery. So this is, we created the pipeline. This time we took the lessons we learned from the data lake and make it a bit better. So I can show you this pipeline a little bit. Just a lot of things. So I will not try to harass you or bore you with so much information about it. But it also has the same problem as this extra peak of data happening every day in the morning. But as you can see here, this is a typical ATL. In this case, it's not a straight pipeline. You have diversions. And one thing I didn't mention that you can see the actual or more or less accurate amount of traffic you're having per second, which is pretty nice. But in this case, in this pipeline, we are simply getting information for our pops up a subscription, and we parse the documentation, the document, sorry, we assign a schema and try to put it, sort of speaking, back into, into BigQuery, which is this last step going on here. And for every diversion we get here, we collect the errors happening at that point on the stage. So we can keep them somewhere, and we can analyze what's happened. And I think that's pretty important, because something that you will face whenever you build a warehouse, data failing to be inserted, and you have to investigate why. Usually, a typical error we have is like people add new attributes to a particular model. Those attributes are not reflected in the BigQuery schema, and they fail to be inserted. BigQuery will complain about it. So for those cases, we have another Google product, which is Data Store, which is like the NoSQL database they have. It would be like the equivalent to CouchDB itself. So we keep those blobs of data out of there. We can query them and see why they fail in an easy manner and recover them eventually. And that's pretty much it about. 1 second. So in the end, this is the architecture we have for the warehouse. Okay. The nice thing about this pipeline, the warehouse builder, which is what I just showed you before, is that it can not only run from traffic in a stream mode coming out of PubSub, but it can also read data from the data lake, and you can run like batch jobs to populate all data back into your warehouse based on the data you have on the lake. And also then, as I mentioned, you have the warehouse itself, and also the error storage in Data Store, where we can recover our error data. So this is like the third step out of this data infrastructure we have created in 1 year. So we say, okay, we have the data lake, we have the data warehouse, we can run queries, we can access our data, we can create nice dashboards. But the next question is, how do we help our data scientists and other people doing machine learning in the company to run their machine models in a proper way? So we came up with an idea which is not ours. We're not inventing the wheel here. We are basing this infrastructure, this piece of infrastructure, in Uber's Michelangelo machine learning platform, which simply defines the idea of we can have features, and the feature is a piece of aggregated data. Okay, we can have like based on different inputs, we can aggregate, create new data out of it, or even we can have the output of a machine learning model as another feature. Okay, we have a machine learning model, we provide it with data, and the output of this execution of a machine learning model, it's the feature itself. So we need a place where to store the features we were computing on a pipeline. We created a set of pipelines to compute those aggregates and execute those machine learning models, and we need to store them in a place where they can be quickly consumed by any service within the company. Okay. So this is basically what the architecture looks like. Pretty much, we have our friends, the data lake and PubSub as the source of data. We have created a set of data flow pipelines to compute those features. Sorry, those features once they're computed, they are stored on a database in Bigtable, which is another Google Cloud product. It's a Bigtable for those of you who do not know it. It's like the big brother of Cassandra, self-hosted, self-managed by Google, or Happy Days. And it provides a pretty neat feature, which is that you can access data pretty quickly by key, but you can also run like time series queries. So you can have like different features based in time. Like for instance, the amounts of working hours a driver had in the last year, or the last week, the last day. Okay? You can aggregate, do micro aggregations, and then fetch in a row all the data for a particular driver, for instance, or a particular user. And this is pretty, just to give you a couple of examples, you can have like offline pipelines and online pipelines. They call it offline pipelines for those who are running in batch. Online are those who are running in stream mode. So one of the examples we have at Cabify about online pipelining is what I just mentioned. We compute the working hours and some other statistic information about drivers, how they are performing, because we are improving our current bonus providing subsystem. It's a work in progress at the moment. But we want to provide the drivers with real-time statistical data so they can, for instance, know if they're close to getting a bonus or a reward, because we use gamification in some parts of the process. Because currently this process is run like manually, not manually, but automatically every once a week. There is a huge job run by a person who will say, okay, we'll run a lot of queries, get all the drivers who worked the last week, and assign bonuses based on some particular rules. And this is not really the way to go if you want to engage your drivers, which are the base of our business in the end, right? So if you're a driver and you see in your screen that you are like 30 minutes away of getting a bonus, chances that you will stay connected are higher if you can see it live on your screen. So that's the purpose of those online pipelines we build at the moment. Another example of an offline pipeline, some of my colleagues here might be better suited to explain it, but we realized a few time ago that some marketing campaigns were not targeting the appropriate users. For instance, we noticed that there are lots of users who use the service quite a lot, but they have never paid a cent for it. So they just keep waiting for the next voucher to come. They will use the voucher and then keep dormant until the next voucher comes. So we created a pipeline that will compute how alive a user is, how likely a user is for being using our service. So we can target appropriate drivers based on that information. And that's based on a machine learning model that runs on one of those pipelines. So typical question is like, okay, you have these three like cornerstones of the Cabify's data infrastructure. What's next? There's a lot of work to keep growing and to keep going. We have to continue building Michelangelo-like platform for machine learning. So the next step will be to create a proper infrastructure, a proper set of machines or environments where our data scientists are able to train their models, see how their models are behaving in production, get some key KPIs from those models, and see if they have to redeploy any change on them. And also we need a proper API or interface to access those machine learning models, because I just didn't mention here in this graphic, this piece of here, we're currently, for every particular project, we are creating an API which runs on a Kubernetes cluster. So we have not standardized yet how those APIs should be built, how they should be deployed. We have like customized APIs to serve particular features from the feature store, but we are already working on how to create a common API to get data from the feature store. So that will be the second part of this. And all this will have not been possible without an awesome team. So I would like to take the chance to thank Mario, Carlos, Jose, Alberto, and Guillermo for the awesome job they've done so far. Mario and Castro, they're not anymore with us. They decided to fly away to find a better life. We miss them. And that's pretty much it. I don't know if you have any question. And I don't want to lose the chance to gather people. We are looking for data engineers. So, you know, if we have some time for questions or.
Yeah. So what about versioning of schemas?
Yeah,
Like whenever you need add new attributes, how do you handle this?
Yeah, that's an interesting question. Currently, we do it a bit manually. We have set up a process in which we encourage people to warn us in advance when they change something. They also have access to the repositories. It's simply a Git repository. So they have access to the repositories. They can do the change and request, make a pull request on a change. But we recently moved to GitLab, and we have access to pretty nice CI tools. And we are already working on creating a CI system in which we can have anyone being able to change a model. That model will be, when pushed on a particular branch, will trigger a CI process that will check that model against a testing environment. If that's okay, heads up, you merge into production, sorry, into master, and that rolls over into production, into the production data warehouse. So that's but it's still an idea we have. We're working to get it. Okay.
So it's been interesting to check the traces from where the data, which was the origin of the data. So I put some ideas from Cabify. Have you the team thought about using some tool like Apache Atlas or some tools that could trace which is the origin or source of the data?
In order to just to understand, we haven't checked. I didn't know what Apache Atlas is, so that's a good thing to investigate and check. Thanks for the tip.
I am wondering, why do you use Google platform instead of AWS or Azure? What is
the thing is that
main reasons behind?
Yeah, well, the main reasons is like we were the first data engineer we have at Cabify, which is Mario Castro. He was really a fan of Google Cloud, and we had the other members of the team. We had prior experience on it, and when I joined the company, he was doing a lot of testing with TensorFlow, Kubernetes, lots of things. And but there wasn't a particular reason. We simply felt more comfortable with that. We could have decided to go for a similar approach in AWS. So because I was checking a comparison matrix there, like most of the products I've talked about here have an equivalent like in AWS. So it's a matter of evaluate the pricing and see if that fits your needs. In our case, we had budget, and we were like really focused on this TensorFlow running under this container engine. So we decided to stay there.
Any other questions?
So what's the current status of Python, the Python SDK for Apache Beam at this moment? Because when I saw it like a year ago, and it was pretty much abandoned at all.
Yeah, the last time we checked, it was like they were about to release like version 2.10 for the Java SDK, and the Python SDK was like in 2.6, 2.7, something like that, like very far away. We had to build our own. For instance, we have a reader for Bigtable. It was not at the moment, so we had to build our own reader out of Apache Beam. And we are thinking to put it pretty and to make it publicly available, because we were in discussions. We have some. We are in the Slack chat rooms about the Apache's Beam project, and we have been asking for advice. We had already contributed in the in the Java SDK part. But yeah, we would like to contribute this piece of Bigtable connector, but we didn't have time to make it pretty. I don't feel like really comfortable yet, but we're using it in production, so it's working. Pretty.
Question: how do non-tech teams use this data lake? Like, what would be a
usually you have to guide them to install the proper tooling, because the frontline access to the data lake usually is you can access it either by the interface at the Google Cloud console, but you can use a GSUtil, which is part of the G-Cloud tool suite. So usually when somebody non-technical comes to us for advice, we teach them how to use it, because in the end it's like running a typical, no, not a SQL, but you just copy files to your desktop and you then access or grab, or in the end you have to be some sort of technical if you want to read the raw data, because it's in JSON format. So you have to understand what JSON is, how to split it in parts and access.
All right, so no more questions. There's some beers, there's some more beer, and there's pizza coming. I think it's gonna come in around 5-10 minutes. And then if you wanna hang out, we're gonna be here for 30, 40, 1 hour, 30, 40 minutes, 1 hour. And you're welcome to stay here a little bit and talk some data engineer. Thank you very much.
Thank you.